I want to start discussing this, in my opinion, beautiful paper written by an Italian physicist, but actually she also works in the field of mathematics, as far as I know, at least applied mathematics. And her name is Ginestra Bianconi, that you see spelled out here. And she was able to derive gravity from quantum entropy. So this is actually something important and in my opinion very original, because the idea that gravity can be connected to entropy is not new. However, the important contribution by Ginestra Bianconi is due to the fact that she was able to start from quantum entropy, from the quantum definition of entropy, where we start with operators, and we have something like minus the operator, some operator. In quantum mechanics, we have rho, the density matrix, and then we have the logarithm of the density matrix, and you take the trace of that. So that's how you can define entropy, and I have already discussed in previous videos how it is possible to define entropy like this, and why actually it is possible to define entropy like this. Now, in this case, I want to get into the technicalities of the article. I want to start doing the derivations that are proposed in the article, but I want to go deeper, and I want to show you all the important mathematics behind this paper, because in my opinion it is very important, and it opens up new ways to look at physics and not just at mathematics. So we are going to see some interesting mathematics, but also we are going to see some interesting physics behind this mathematics that, of course, has not been proved to be correct yet, because you have to be able to carry out experiments and so on. So I don't want to get into that kind of stuff, but I want to show you the beautiful ideas behind it. So I hope that the message will come across, and you can read the article yourself. So I will not read the article. I will not let's say do the derivations in the same way that Ginestra Bianconi does. But what I want to do, I mean, my objective with this series of videos is to fill in the gaps, because some derivations are not provided. So you start from some formulas, and then some other formulas are given, and probably you might be interested in seeing the derivations carried out completely. And that's what I want to do. So let's start from the first important concept, which is that of eigenvalues and logarithm of rank 2 tensors. And as we progress through the article, we will see more and more important concepts arise. So I don't want to start discussing the ideas of provided by Ginestra Bianconi and what she's going to obtain in the article. I want to start from some mathematics, and then as we move on, I want to show you some interesting concepts, how these concepts arise. So I want to do something constructive. I don't want to start from the results and then giving the proof or the proofs. I want to start from the basic mathematics, and little by little we will discover more and more concepts, and we will introduce more and more concepts as well, to be able to find a connection between gravity and quantum entropy. So in order to do that, we have to introduce the concept of eigenvalues and logarithm of rank 2 tensors. In particular, I will denote our tensor, and in particular this will be an operator that I will call g hat mu nu. Sometimes I will not put the hat, but never mind. So in this case I will do that to start from the fact that we have some operator with two indices, two subscripts, and this means that this object here should also be considered as a rank 2 covariant tensor. We can act with this object on a vector that I will use the same notation used by Ginestra. It's written as v lambda. I will explain it, but just give me some time. V lambda nu, like this. So this is a vector associated to the eigenvalue lambda. So this is an eigenvector. The eigenvector associated to the eigenvalue lambda, and in particular it is the nu component of this vector. So I put the superscript because in this case we are going to sum over nu. So this is basically just like, so if we use matrix notation, we have a matrix G because it has two indices, so we can think of this as a matrix as well, acting on some vector V which depends on this superscript lambda, but we are not going to sum over lambda. This is just an indication of the fact that it is an eigenvector associated to the eigenvalue lambda, where lambda is just a scalar. And by definition, so we define this to be lambda, and then we have the vector itself. But if we want the notation to be covariant, in particular we want to use tensors, we can write v mu, and then here of course we still put lambda, because if we change lambda then the eigenvector changes. That's why we are using this notation. And so this definition here is something that should be familiar to you. It is not something surprising, but we will see that if we want to impose covariance, we are going to see that something interesting will happen, and of course this is just the beginning. I will introduce the concepts little by little, and this is just the same order in which Ginestra Bianconi does that. So at first, this is just an introductory lecture, and it will be quite similar to what you see in the article. In particular, this is the second paragraph. I don't know if I can call it paragraph, but there is the introduction part, the introductory part, which is the introduction, so the first part, and then there is the second part where, it's titled Motivation of the Theory and Preliminary Considerations. So I will try to follow the order provided by Ginestra in her article, and at first you will see that the concepts will be quite similar to what you can already read in the article, but I will provide more insights, and then in the later parts, in the middle and in the later parts, I will have to introduce some more mathematics. In particular, I will have to show you some more steps, because the mathematical steps are actually omitted here and there. So I want to fill the gaps, as I said. Now, I will of course assume that tensor calculus is known, and so if you lack some prerequisites, I hope that you can consult a book on tensors if necessary, and I also take for granted the fact that you already know some general relativity, because after all we are going to use general relativity. This will come later, and also let's say forms, differential forms will be important, and if necessary I will put some more videos here and there to tackle some concepts. I have already created some videos on differential forms, so I will not really do any video related to differential forms here, but I will give more details wherever necessary. And if I have not explained some concepts in previous videos, I will fill the gaps in here. But you have to be aware that I have already explained technical mathematical details like tensors in other courses, in other videos. So this is something more advanced, and you need to know this kind of stuffs that we are starting with. Now I can rewrite this equation like this if I use the metric tensor G sigma nu, so this is just the metric tensor that you see in general relativity as well. If I act with that on G mu sigma, so this G here is something different. In principle, it can be a generic rank 2 tensor. And so I have simply rewritten this part, because if you multiply, I mean, if you act with the metric tensor on G mu sigma like this, you get, so here you get G hat mu nu. So the nu here is actually a superscript in this case. And I can either put the superscript here and the subscript here, or vice versa. So if I want, I can raise this nu here, and I can lower this nu here, and this is just due to the usual rules that you have in tensor calculus. So I will not get back to that here. So I'm assuming that you are familiar with this kind of notation, and then here I can write v lambda nu, and this in this case this is just a lower nu, and this is equal to lambda v mu lambda like this. So the eigenvalue problem can also be written like this, as you can see, where this metric tensor here, since it has superscripts, you can define it to be the inverse metric tensor, if you recall, because in general relativity we have G mu nu with the subscripts, and this is just the metric tensor itself. But if we raise the indices like this, then this would be the inverse. In matrix notation, here you can write G hat G inverse acting on the vector V, and of course here we should put lambda, but let me drop the lambda here just in this case, and then we have lambda V like this. So you can see that in matrix notation we can also make the inverse metric tensor appear, and this is due to the fact that we have subscripts and superscripts, and the subscripts are related to covariance, whereas the superscripts are related to contravariance. So since we can have either covariance or contravariance, you will see that this metric tensor will appear very often. So we have to be careful, because if you start writing the matrix expression from here, here you can see that you have a contravariant object, whereas here you have a covariant object. So depending on how you define the matrix G, and you can get the metric tensor or not, because if you define G as for example G mu nu, so with an upper index and a lower index, then the metric tensor does not appear, if you think about it, because this G inverse was defined like this. So actually it is defined as G mu sigma G sigma nu, and this can be defined as G mu nu. So you can see that if you use mixed indices like this, or in some other cases, depending on your definitions, you might define the indices also like this. It depends on your definition, and you have to be, of course, consistent with your notation. So at the moment I can also cancel this expression to avoid increasing the level of confusion that might overwhelm you. Hopefully that's not the case, because you have to be aware that we are going to use tensors and tensor calculus and so on. So if you have already encountered tensors, like in courses on general relativity, you should be familiar with this notation, and this should not be surprising to you. So if we choose G hat to be the metric tensor, you can see quite easily that the eigenvalue associated to the metric tensor G would be equal to 1. And this is quite easy to see, because if we simply replace in this formula G hat with a G, so we have G mu sigma G sigma nu, Then we have v lambda nu equal to lambda v mu lambda. Well, of course, due to tensor calculus, this would be the Kronecker delta mu nu, which is equal to g nu mu. So the metric tensor with mixed indices is equal to the Kronecker delta. This is another property of the metric tensor, well known from general relativity. And you can see that when we multiply the Kronecker delta and we sum over nu, and we multiply it with this vector, we get v lambda mu, and this must be equal to lambda times v mu lambda. But of course, if they must be equal, it means that lambda must be equal to 1. So this is the property of the metric tensor in this case. So you can see that the eigenvalues associated to the metric tensor are equal to 1, and this is one of the first few concepts described, or actually derived, if you want, by Ginestra Bianconi in her article. And then she starts introducing the logarithm, the natural logarithm of the operator g, which is, if you want, g mu nu, so we can write that in index notation. And it's like taking, so it's similar to taking the natural logarithm of a matrix that I've already introduced multiple times. And I will have to tackle this also in subsequent videos as well, because this will appear throughout the article. So it's very important to understand how to deal with the natural logarithm, with the logarithm in general. So if it's natural or not, it's not actually important. We will assume that the basis for the logarithm will be the Euler number. So this would be log e, if you want, of some quantity, and therefore e is the natural basis for the logarithm, and we call it the natural logarithm. And this can be written, the natural logarithm of a tensor with two subscripts, so it's like considering a matrix. It can be written as a summation, so we have to sum over lambda over the eigenvalues, and we have the logarithm of lambda, v mu lambda, v nu lambda. So I will describe it more in detail in a moment. This is something that Ginestra writes in her article, and actually she does not write the summation, but it's implicit in the formula, because we have to sum over lambda. And if we use the well-known matrix and vector notation, we can rewrite the natural logarithm of this matrix G in the following fashion. So you can think that here we have a tensor product between two vectors, v and v. So this should start being familiar, or becoming familiar little by little. So first let me write down summation over lambda, or if you want, you can write the summation also like this, summation over I. Here we can write the natural log of lambda sub I, and then we have v sub I, tensor product v sub I, where the index I is something that is related to the eigenvalue. So if we say lambda 1 is associated to v1, lambda 2 is associated to v2, and so on. Now the eigenvectors vi, vj are orthonormal, so vi dot product vj is equal to delta ij, and you can also write this expression in the following fashion. So you have a matrix of the kind v1 written as a column, v2 written as a column, dot dot dot. Then here we have a diagonal matrix with the eigenvalues, which are logarithm of lambda 1, logarithm of lambda 2, dot dot dot, and then you have a bunch of zeros outside of the diagonal, and then here you have the transpose of this matrix, v1, v2, written as so this is written as a row, and this is also written as a row, dot dot dot. You get the idea. And if you call this matrix V transpose, this would be the matrix V, and V transpose V would be equal to the identity, which is simply telling you this fact. So this matrices, or this matrix V is orthogonal. It's an orthogonal matrix, and if you do the multiplication here, then it's quite simple to check that you can decompose this part just like written here, because you can write the matrix V transpose. If you want, let's write V transpose. Then we can take the natural log of lambda 1, which multiplies the matrix 1 0 0 0, so you have all zeros outside of the diagonal, and also, I mean, the only non-zero element is this one, and then you have V plus, you get the idea, V transpose natural log lambda 2 0 1 0 0 dot dot dot. Here of course you have dots, and also outside of the diagonal V. And then when you multiply this matrix by V and V transpose, here you're going to get simply natural log lambda 1 V1 written as a column, V1 written as a row, and this would be the tensor product between V1 and V1. And similarly here for this one you will get the second term in this summation, and so on. You get the idea. But if we rewrite the summation like this should be more familiar, and in particular let's call this, so we can call this the natural log of lambda, where lambda is the matrix of eigenvalues lambda 1 lambda 2 dot 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 on the diagonal. So since it's a diagonal matrix, the logarithm of a diagonal matrix is just the logarithm, so we have to take the logarithm on the diagonal. Basically it's quite simple. Now this expression here can also be written as V transpose natural log of lambda V, where the natural log of lambda, as I said, is a diagonal matrix of this kind. So you calculate simply the logarithm of the eigenvalues, and then you still have zeros outside of the diagonal. And this is how you can calculate the logarithm of a generic matrix G. So you diagonalize the matrix in this form, and you can calculate the logarithm quite easily from the eigenvalues. Now it is also possible to write, for example, the natural log of G inverse, and if we consider the indices mu and nu, so this would be a matrix with indices mu and nu. I will put the superscripts just because this is the inverse matrix, but you have to understand that, I mean, it's important to understand that we have two indices, and because we have a matrix, and this can be written in a very similar fashion. So you have a summation over lambda, I will use the following notation, V lambda, so this is the eigenvalue, in particular it is the mu component of that, and then we have V lambda nu, so this is like a tensor product because we have the two indices that make up our matrix. And then here we have the natural log of the eigenvalue, the generic eigenvalue associated to G inverse. But we can write this as 1 over lambda, because the generic eigenvalue associated to this matrix is the inverse of the eigenvalue associated to G. So if G, for example, has an eigenvalue lambda, we will have 1 over lambda for G inverse. It's a simple property of inverse matrices, and therefore this can also be written as minus the natural log lambda due to the properties of logarithms. And so we can use the following expansion. But it is also possible to write, for example, the expression for the inverse matrix itself without the natural log, and of course here we would have the following expression. we have something like this. So this is a multiplication, or if you want, we can also write it as lambda inverse here. So you have the following expression. You have to sum over lambda, so you have to sum over the eigenvalues, and this is how you can write it. And another important property that we need, and it's very important to understand because Ginestra Bianconi uses it throughout her article, so it's used in almost every section, and in particular it's the trace of the matrix, or I can say operator, or I can say tensor if you want. As long as you don't get confused, we can use this kind of definition interchangeably. So we can either say tensor, operator, or matrix, sometimes almost interchangeably. And the trace of this tensor should be defined, of course, as the summation over the eigenvalues of the eigenvalues themselves. So we can either write it like this, or sometimes I can also write it like this, summation over I, lambda I, if we denote the eigenvalues as lambda 1, lambda 2, and so on. So this notation or this notation are, I will consider them to be interchangeable. And this trace can also be calculated in another way, of course, by using the properties of tensors. In general relativity, we have something like this: G mu nu times G mu nu. So this is the inverse metric tensor, and then we have to sum over mu and over nu, like this. And this can also be expressed in another manner, for example, like this. I'm going to use the following notation: trace sub m, and I will explain what this m means. Some other times, also in Ginestra Bianconi article, instead of having m, we have f. So we can either see m or trace f, and I will tell you in a moment what this means. And here we have G inverse. So basically, I have already shown you that we can express, so we can make the inverse metric tensor appear, as you can see here. And therefore, here we calculate a trace, but this trace it should be intended in a slightly different manner. It means that we are taking the trace in some kind of Euclidean space, or if you want, flat space. So if you see F, it stands for flat, and M, it is just some kind of notation. It is something similar. I don't want to get into the technicalities here. It's important you understand what this means. It means this. So you take the trace sub M. Now if you use index notation, G is written as G alpha beta, for example, and G inverse would be G beta gamma. So I'm using index notation, so you can see that this index is different from this one, because in general, when we consider matrix multiplication, we only sum over the index in between. So it's like the usual matrix multiplication. You multiply the row of the first matrix by the column of the second matrix, and so on. So it's the usual product rule for matrices. And when you take the trace, you have to contract alpha with gamma. And in Euclidean space, you do the contraction by using the identity matrix, or in particular by using the Kronecker delta. So this would mean G alpha beta, G beta gamma, and then here we have G alpha gamma. So we sum over alpha over gamma and over alpha, and since this is a metric tensor with mixed indices, this is simply equal to the Kronecker delta. So here I can replace G with the Kronecker delta, like this. And so it's important to understand the difference between this trace and this kind of trace here. They are very similar, but in the second trace with the subscript M or F, as I said, you have to contract, you have to do the contraction by using the Kronecker delta. So it's as if you are in Euclidean space in the second case, whereas in here, when you take this trace, you see that we are in this could be curved space. It's non-Euclidean. So it's important you understand the difference. because this will appear quite often, but basically it's still the same. So with this you have some kind of mixed indices, and so you still have the metric tensor, but with mixed indices the metric tensor becomes the Kronecker delta. And this is the generic idea, and it's important to understand because this will appear throughout the course, throughout the lectures if you want, because the trace of this operator is very important in Ginestra Bianconi's article, and it is part also of the definition of the entropy, of the quantum entropy. So we need to understand how to calculate traces very accurately. So you have to differentiate between this kind of trace and this kind of trace here that, as I said, will appear. But it's I mean, this is it for this video, and we will proceed in the following.